The whole object of the course is to try to examine the structure of effective or good reasoning. But up until now, you've gotten nothing but the basic tools. As of this week, in Chapter 5, we're going to actually begin to sort of work out some, at the beginning, very simple lines of reasoning and see how these tools that you've learned so far can be used to perform derivations in SL, sentence logic. Let me start with a very simple one indeed. And this is partly what I want to do today, is to sort of get you acquainted with the machinery and with the way you'll be expected to perform these derivations in the Logic Cafe. This is going to look a little bit different up there in the cafe, but you'll get the basic ideas. Anyone actually look through any of the stuff in Chapter 5 yet? Okay, good. Then I won't be repeating anything, but you'll see this stuff repeated in the cafe, in the tutorials, and in the exercises. But let's say we're trying to derive L from these two premises. Now, this is a simple enough one. It should seem pretty obvious that you can. If you've got A horseshoe L, or if A then L, and if you also know A and B, then in a couple of steps you can get L. But what we're going to try and do is to show just exactly how that's to be done and how they want to how they want you to proceed. We'll do a couple of them for this problem. The first one is what we call ampersand elimination, and the abbreviation for that is right there, ampersand, capital E. And once again, this is in standard form. This is the argument form that we I think learned in week 1, if not I think it was week 1. Is we've got a premise above the line and the conclusion below, and all this says is that you have P ampersand Q. You're entitled to infer P, and that's for any atomic or molecular sentences. Those P's and Q's stand for any sentence at all, no matter how long, any legitimate sentence in SL. So if you have P and Q, you can legitimately draw out P. And also, if you have P and Q, of course, you can legitimately draw out Q. So that's the rule ampersand elimination, and I think that should be fairly plain. And the second one we'll need for this first derivation is horseshoe elimination, or horseshoe E. And once again, this calls for 2 lines. Notice that in using ampersand elimination, you just refer to 1 line. You refer to the line if you're going to. I'll illustrate this in a second. But to pull out the A, for example, you'll refer over here to line 2, ampersand elimination. That's the justification, and then you can put your A down. And here you need 2 lines to make use of the horseshoe elimination. P horseshoe Q, P, therefore Q. And once again, the P's and Q's stand for any sentences at all, as long as the Q is the same in both cases. But if you have a material implication, P horseshoe Q, and if you have the antecedent, you're allowed to infer the consequent. Now, both of those rules should be pretty transparent and pretty obvious. And then the way to write this down is what I would do is first I would go from line 2. You put the line down, and then I'm going to once again use my little fake ampersand because I hate drawing ampersands. You don't have to either when you're required to write. But this is ampersand elimination from line 2, and I'm going to pull out the A. And then you could do it either way. It doesn't matter how you list these things, but I usually put the antecedent first, comma. That's line 3, and line 1 is the material implication. So from line 3 and 1 by horseshoe elimination, we get our L. QED. Okay, is that pretty plain? All right, then we'll need one more rule. For this morning, and this is ampersand introduction. And basically, for all of our connectives, we're going to have rules of elimination and rules of introduction. And so the abbreviation for ampersand introduction is ampersand I, and for that you need 2 lines. You need a sentence, two different sentences of our language, SL, and you're allowed to conjoin them in the conclusion if you have these 2 lines somewhere earlier in the derivation. Now these can be anywhere in the derivation. As long as you've established, now these things are established because they're premises, they're assumptions. That's what we're beginning with. We start with those things. And then as you move down, anytime you've established something in the main derivation column, we'll later be working with further columns and sort of sub-derivations when things get more complicated. But for now, we've only got the one derivation column. Anything we've established up there is a legitimate, we've proved it, at least based on the premises, and we're able to work on it with our rules of inference. So we've got 3, and I'll do one more demonstration, then I'll turn you loose on a couple of these things. Let's say what we're trying to derive is S and M, which is always useful to derive. But in any case, what I would do is I would start with 1 by ampersand elimination, and I would bring this down. Notice we've got a molecular sentence up there in line, or 2, a molecular sentence is the left conjunct in line 1. So that's what we bring down. It conjoins the parentheses curl T horseshoe S with M. So those are the 2 conjuncts. We bring down the first. We could bring down either one. And then with 2 and 3 by horseshoe elimination, we get S. And then we have to do this one step at a time. You can see obviously what's to be done, but in order to just sort of be as rigorous as possible, we need to make sure that we only take one step at a time. So the next step is 1 by ampersand elimination again. This time we bring down the M. And finally, by 4 and 5 by ampersand introduction, we get what we're trying to prove, S and M. Okay, now do you see how that all works? Are there any questions at all about the routine? About you need to take only one step at a time in order to actually demonstrate, because our rules require that we unpack things. Sometimes it'll seem very, very dumb to have to do particular steps. Like I think one of the problems that you're going to confront in the Logic Cafe, they want you to show that from M equivalent to N, or something like that, show that you can prove the flip-flop, N equivalent to M. In other words, just turn it, it's obvious, you shouldn't have to, and later on we'll get a rule that will simply permit it, but for now, just as an exercise in the Logic Cafe, they'll want you to demonstrate this, that from M equivalent to N, in several steps, demonstrate that N is equivalent to M, that it goes the other way around too. All right. Now, if you've got no questions, what I want you to do is to try out this one. You have to derive P and follow this step-by-step method. Oh, and I'll tell you what I'll do. So I don't have to keep paging back to the rules, there's the 3 rules. Can you pass this around? Eventually, you'll have a whole toolbox of these rules, and I'll need you to memorize their names and remember what they are so that you can do these derivations without cheat sheets. Okay, Eric, what do I put on line 4?
It's on 1 with horseshoe elimination, L and N.
Is that what you do?
That's what I did.
Okay, 1. How can you do that? What's the antecedent of 1?
L and N.
Do you have that?
Yeah.
No.
Oh.
So the first thing you need to get that antecedent, but you need from 2 and 3 using what rule? Ampersand introduction. Then we get L and N. And that's part of what I want to run through some of these exercises with you. Just make sure you're comfortable with what you have to do. And then, using what, Eric? I got to have 2 lines for horseshoe elimination.
Not sure.
Okay, it's number 4 and number 1. So that's the antecedent, that's the conditional, 4 and 1. By horseshoe elimination, then I get my P. Correct? Any questions about that? Once again, you need to do these things one at a time. Okay, here's another one. Derive D and B, please, on this one. Okay, Greg, what do I do on what's the first line? Or line 4, I mean.
I did ampersand elimination on line 1.
So 1, ampersand elimination. And which you got the A?
Yes.
Okay, then?
And then I did horseshoe elimination on 2 using line 4 to get C.
Okay.
The same thing to get D, horseshoe elimination using C to get D.
So using line 5
Yeah.
and line
Line
3 to get D. Then?
And then I used an ampersand elimination on line 1 to get B. And an ampersand introduction on 6 and 7 to get D and B.
Okay, is that clear? Any questions about any of that? Okay, here's another one. Let's see, Pete. What's line 3? Or what's your line 3? There's a variety of different orders to do this in, but what did you do on line 3?
L.
Pardon?
I put down L.
So what's the line number you refer to?
2 and E.
Okay, then?
Then, if L, then M, which would be 1 and E.
Then?
If M, then S, which is also 1 and E.
Okay.
And then M, which is 3, 4, horseshoe E. And S, 5, 6, horseshoe E.
Okay. Josh.
Does order necessarily matter? Because I had similar steps, but I did like.
In this, I mean, sometimes it might, but no, you could have done it differently. I probably myself would have taken the L out, and then the L horseshoe M, and then I would have got the M. And then but it doesn't matter what. In this case, that order doesn't matter. As long as you've got a line earlier in the proof to work on, then you're fine. Any other questions about that one? Okay, I think try this one to derive L ampersand curl F. All right, Kevin, what'd you do on line 3?
Line 3, I said using line 1 and ampersand elimination, I got not F.
Not F.
And then using line 1 with ampersand elimination, I got not G. Then using lines 2 and 4 and horseshoe elimination, I got L. And then 5 and 3, using ampersand elimination, I got L and not F.
Ampersand introduction. Okay, any questions about that one? Okay, so you see how they go, and that it's necessary to write the lines and then the rule over there on the justification side. It's necessary to remember commas. Later on, we'll be doing some other sorts of derivations that require another element of punctuation. You're going to have a dash, or sometimes there'll be sort of conditional proofs or indirect proofs or sub-derivations, as they're called in Logic Cafe. But the punctuation is necessary, and the line numbers are necessary. Most of the time, the order in which you write the line numbers doesn't matter. You could do it either way. You could put 4-2 horseshoe elimination in line 5. That would have been fine. This first rule is probably the most obvious thing in the world. You might wonder, why on earth would we ever need anything like this rule? Reiteration, which means literally saying it again. At the end of class today, we're going to start talking about conditional proofs and sub-derivations. And I won't say anything more about that right at this instance, but this rule comes in handy for those particular techniques. And it just means that if you've got any line, any sentence at all, someplace in the proof, you're perfectly entitled to infer it, in other words, to repeat it elsewhere later on in the proof. So if you've got it in a main derivation line, you can move it over, you could repeat it in a sub-derivation column. And that's, you'll see what I mean in a minute when we get to that. But so this rule is just means that from P, you're entitled to infer P, and that's not particularly complicated. This is vel introduction, or wedge introduction, or V introduction, whatever you want to call it, or introduction. And this might seem counterintuitive at first, but it shouldn't be if you think about it. From P, any sentence at all, P, it could be an atomic sentence, or it could be a very, very complex molecular sentence. But from any sentence P, you're entitled to infer P or Q. And similarly, from any sentence Q, you're entitled to infer P or Q. So the order doesn't matter. And it just means if you know P, well, then you know P or anything else on the planet. It could be a contradiction. It could be anything in the world. If you know P, you're entitled to say, well, then either it's true, or then you can say anything you want. This other thing is true. It could be impossible for the other thing to be true, but you know that either it's true or P is true because you know that P is true. Does that make sense? And that'll come in handy sometimes when you're trying to prove or derive some very exotic-looking sorts of things. You can just simply introduce something like, the exotic sort of thing that you want to give reference to into the line in this particular way. So it will become useful as we go along. Okay, now this is more complicated. but again, it makes good logical sense, I think, so it shouldn't throw you. This requires 3 lines to do an OR elimination. If you have P or Q, and if you can show that each of those 2 things imply R, you know one of those is true, they both reply R, you can conclude R. Now oddly, you're eliminating an OR, a vel, but you know, you're not coming up with any of those things in the conclusion line. But still, it's the name of the rule is OR elimination because that's what you're doing. You're showing how to get rid of an OR. If you can show that each of the 2 things in a disjunction, each of the 2 disjuncts, both imply any particular thing, then you're entitled to conclude that particular thing. Does that make sense? Okay. There are a variety of ways of accomplishing this that we'll get to later on in the course. I don't. It's either this week or next week. I think we get to it, but this is the one that the way of introducing the triple bar, the equivalency. This is the way that we'll use at least at first, and then there's other options later. But if you have on any 2 lines of the proof earlier on, if you've already got P horseshoe Q and then the opposite, Q horseshoe P, then what you've got is an if and only if situation, right? And so you're entitled to conclude on a later line, any later line, P identical to Q. And triple bar elimination, as you might expect, works like horseshoe elimination, but both ways this time. If you've got P triple bar Q and P, then you're entitled to conclude Q, and the other way around too. If you have Q, you're entitled to conclude P. That simply reflects the fact that you've got implications going both ways in an equivalency statement, triple bar. All right, now, what I want to do is to sort of demonstrate this in action. What you're trying, I'm going to work on this myself. You don't need to start on your own. Right? I'll give you another one in a second, or maybe I'll get to another one in a second. But in this particular case, the objective is to derive U ampersand L triple bar S. I'm looking for suggestions from any of you as to what a good first move might be. Adam?
Equivalence introduction on lines 2 and 3.
Okay, let's try that, see where that gets us. So it's from 2 and 3. And what are we going to put down there?
L is equivalent to S.
All right. So that's one of the 2 things we want to conjoin. So that's that's a good start. How are we going to get that U? Because we want to finally. I mean, the way you see that on the last line, you're going to want to have U in an earlier line, and you're going to have L triple bar S, which we now have in an earlier line, so that you can conjoin them. What's the next thing, Nathan?
Do an OR introduction on line 2. So you have A or L.
So it only requires 1 line to do an OR introduction. And so then what are we going to have?
A or L implies S.
All right. Then obviously enough, I think the next step, you've built that up well. What's the next step? Somebody else? Greg?
Take the triple bar out of line 1 using the one you just did, line 5.
I can't quite hear you, Greg.
Take the triple bar out of line 1.
So
using
triple
line
bar
5.
elimination.
Yeah.
Right. And what lines are we going to refer to?
1 and 5
Okay. I'm going to, because I have this.
to get U.
You get U. Right? And now what? The thing we were aiming at doing, Chris?
A introduction.
Yeah, right. So it's lines 6 and 4, ampersand introduction, and then so we finally get U ampersand L equivalent to S. Is there any questions about that? Again, yeah, Max.
How did you get A in part 5?
How do we get what?
How did you know A was true? It's not like...
You can't. Look at the rule for or introduction,
Oh, yeah, that's right. Never mind.
right? If you have one of them, you can add
Yeah.
anything in the world, and that's why that pays off. In this particular case, it was, we were aiming at something. That was the particular formula on the left side of the triple bar statement number in 1, and so that was the reason why we did that.
Okay. I remember.
But it just came out of the blue as the answer. So where did you get that from? All right. And so, any other questions about this particular derivation? All right. So let's go to the next one. All right. Now, why don't you work on this one yourself? And let me know, please, when you're done. Your objective is to derive x wedge t from all of that mess.
I did the Horseshoe elimination on last 3 and 5.
Okay. 3, 5. Horseshoe elimination. Okay, L wedge S, LRS. And Brad, what's a good thing to do now?
Triple bar elimination on lines 4 and 6 to get X.
And finally, Kevin?
On line 7, using an or introduction, get X or T.
Okay, do you see how that works? All right. Now, that's basically how to deploy these rules. The main thing I wanted to get us to is a slightly trickier technique. It's called a conditional proof. And so far, we've been just using information that we've got on earlier lines to get stuff on later lines, and that's what all those rules of inference permit you to do. But you may remember, even from the very first week, when you had some of those drag proofs, you had to assume stuff. You said, you're coming up with stuff, you're coming right out of the blue. Well, let's just say that we have a sound argument. And then you use the definition of sound and say, well, if A is a sound argument, then it has, it's valid and has true premises, blah, blah, blah. And that's how the proof went. But what you were doing there, you were just supposing something. And it's hard, maybe to see how that is going to play a role in the proof, but it certainly plays a large role in our reasoning processes. And we're trying to figure stuff out. We just say, all right, let's just for the sake of argument, take such and such as an example. What would happen if we did that? And you just sort of proceed that way, and that gives you some very important information that you then can conclude not in just a merely supposing way, but in as having sort of figured something out. So we'll call that a conditional proof, and what it does, it makes use of a supposition to demonstrate what may follow logically from a given sentence, whether it's an atomic sentence or from a compound sentence, a molecular sentence. More often, the molecular sentences give you useful information. And such proofs can be used to introduce conditional statements into the main line of a derivation, or to introduce or eliminate negations, and that's what we're going to try and work with today. All right. And here is the first of these rules. Well, that's not the first of the rule. What that is just the technical term that we're using. Now, we've had justification column in our proofs and a derivation column. What we're going to do in the Logic Cafe is to add another column, or maybe more columns later on. But right, we're going to add another column wherein we will do our supposing, our what-ifing, our reasoning from something that we just come up with as a case to examine, to see what the logical consequences are of it. In a subderivation, what one does is you interrupt the main derivation with a supposition which finally will facilitate a conditional proof. It'll give you some information. As I say, what we use these for, at least by and large, are introducing conditional statements into main lines of derivations or introducing or eliminating negations. All right. So here, finally, is the first rule. This is not written very elegantly because I couldn't figure out a way of typing this out in PowerPoint to make it look the way it looks in the Logic Cafe. It's something more like what you see on the handout page, is the rule for horseshoe introduction. What we do is we suppose the antecedent. Let's say what we want to do is we want to get down to something like this. And the technique will be, in a brand new subderivation column, we'll say, well, what if P? What if P were the case? Then we can use material that we've already derived in the derivation to say, well, since these things over here were true in the main line of the derivation, we can see that if P were the case, then these other things would follow. And if we can get to any sentence Q from P, just by assuming it, then what we've shown is that, well, if P, then Q. We say, all right, what if P? We say, well, if P were the case, using material we've already demonstrated, then we could conclude Q. So, if P, then Q, on the assumptions we've gone through so far. So that's a lot of hand waving. Let's try one. All right. What we're trying to get to is A horseshoe, B wedge, D. That's the objective. And I noticed that line number 2 is indented for some strange reason. Ignore that. The way we do this, I mean, the technique that I sort of indicated in my little hand-waving demonstration a second ago was what, Kevin? I mean, what would you suspect? I'm going to assume something on line 2, but what's it going to be?
We assume B.
What, I'm sorry?
I'm not sure.
Well, what did you say?
You would assume B.
No. The technique is this, and this is a strategic. This is the strategy, not the strategic. This is the strategy that I want you to always think about when you're trying to get at, when you're trying to derive an implication. Almost always, the best way to proceed is to say, well, what if the antecedent were true? And the way we're going to do that is, in the Logic Cafe, he asks you to type A, and then usually the word, and then hit tab, and the word assume pops up. But say assume, then all of this happens automatically in the cafe. In the subderivation column, and this over here, we're going to say, well, what if A were true? And now we stay in this subderivation column until we get what we want. And what is it that we want?
B or D.
Say what?
B or D.
B or D. Because that's what we're trying to show that if A were true, then we could conclude B or D, which just simply means A horseshoe B or D. All right, so, well, if A were true, then what? Yep, 2, 1, by horseshoe elimination, B ampersand C, right? And then what? Pardon? Okay, so from line 3, by ampersand elimination, we get what?
B.
We want B, because we're after B or D, right? Okay, now, it should be obvious, for 4 we use and then here comes, I'm sorry. And then here comes the convention for writing this down in the Logic Cafe. We say 2 through 5 by or introduction. Horseshoe introduction. A, horseshoe, B, wedge, D. Make sense? What we've shown is in our little conditional proof here that if we were to assume A, given what we know already, namely A, horseshoe, B, and C, that if A were true, if A is true, then B or D is true. That's what we proved in the subderivation, which is to say we've proven that A implies B or D. It's just another way of saying if A is true, then B or D is true. So that's how you introduce horseshoes into derivations. Characteristically, you'll do that by using a subderivation. All right. How to introduce a negation, a curl. Once again, we'll be doing this by using a derivation. This is trickier. What we're trying to show is that if we assume P, then we would get a contradiction. So P can't be true. So again, this is in a subderivation. You say, well, what if P? Well, if P were true, you'd get both Q and not Q, some contradiction or another. It could be any contradiction. Well, that means that P can't be true. This is what is sometimes called a reductio ad absurdum kind of argument. And it's a technical term, but it's just, well, look, if that were true, then anything's possible. So that can't be true. It's that kind of reason. So, once again, let's work through this one. This time we're going to actually use one of the examples that we did differently with the drag and drop stuff earlier in the quarter. We're going to demonstrate that a sound argument can't have a false conclusion. And those are the various sentence letters. S means the argument is sound. V says that the argument is valid. T says the argument has all true premises. And false says the argument has a false conclusion. We've got our definitions as premises. A sound argument, if an argument is sound, then it's both valid and has all true premises, right? The second premise is the definition of validity. If an argument is valid, then what? Not true and false. If it's valid, then it's not the case that it has true premises and a false conclusion, right? Okay. So let's work together. Well, let's work together on this one. What if an argument was sound and it had a false conclusion? Okay. Well, then from 3, what's the only rule that we can really use right now is ampersand elimination. We'll use S. And then from 4 and 1, by horseshoe elimination, you get V ampersand T. From 5, take it from there. Somebody? A little louder, Josh.
Ampersand elimination, you can get V.
Yeah, ampersand elimination, you get V. And I don't like this. This isn't going to work.
No, if from here you just do a horseshoe elimination 2 and 6.
Yeah, 6, 2.
And then you get
We don't have a rule for this, though. Right?
How do we have a rule for this?
Say what? Oh, wait. You've got it. You've got not T and F.
Oh, that's okay.
Not T and F. You've got to do one more step.
Yeah.
From 5, ampersand elimination. Now we have T, right? And from 3, ampersand elimination, we have F. And from 8 and 9, ampersand introduction, we have T and F. And there, the contradictions appear in lines 7 and 10, right? So we know that our assumption can't be right because it leads us to contradictory conclusions. So from, and this is the convention for this, from 3 through 10, by curl introduction, we get curl S and F, which proves what we were trying to prove. Correct? Yes, sir. Josh.
From line 7 to 8, when you can just drop the.
No. I didn't do that. Notice that I went from after line 8 is taken from line 5 by ampersand elimination.
Okay.
No, but you cannot just drop. You can't drop the curl. Later on, we'll have a rule that entitles us to interpret this as curl T or curl F. Whoops, curl F. But not now. You can't do that. But those are logically equivalent, as it turns out. That's a rule called De Morgan. You get that next week. Okay. Any questions about this? Any line in this little derivation? Okay. Now, do I have? Yes, I do. I don't have an example to work with, I don't believe, because I ran out of time. But the same technique works for curl elimination. Let's say we're trying to establish something, as complicated a sentence as you please, but it doesn't have a negation sign in front of it. A technique is to assume the opposite of it, the opposite of what you're trying to prove, again, like curl P, and derive a contradiction, and then you can show that that can't be true. So if curl P can't be true, then P is true. So that same technique works there as well. All right, any questions about any of these techniques? Okay, what you'll find is that in these first 4 tutorials, that's all you're responsible for this week in Chapter 5. In these first 4 tutorials, it'll take you through these things and give you ample opportunity to practice with them in derivations. You need to do all of the derivations that you're asked to do, all of the exercises for tutorials 1 through 4. If you are able to, each week, get all of the exercises done in the Logic Cafe, you should do extremely well in the course. Any other questions or comments or knock-knock jokes? Okay, I'm done.